Today I'm with Professor Zhong-Ping Jiang, Professor of Electrical and Computer Engineering at the Tannen School of Engineering at NYU. His research interests include stability theory, robust, adaptive, and distributed nonlinear control, robust, adaptive dynamic programming, and reinforcement learning and their applications to information, mechanical, and biological systems. He's written 6 books, is author or co-author of more than 500 peer-reviewed journal and conference papers. He's also a recipient of the Queen Elizabeth II Fellowship Award from the Australian Research Council, the Career Award from NSF, the JSPS Invitation Fellowship from the Japan Society for the Promotion of Science, the Distinguished Overseas Chinese Scholar Award from the NSF of China, and a bunch of Best Paper Awards as well. He's also served as Deputy Editor-in-Chief, Senior Editor, and Associate Editor for numerous journals, and is a Fellow of the IEEE, IFAC, and CAA, and is among the Calibrating Analytics highly cited researchers. Today's webinar is Learning-Based Control, a tool for autonomous driving, discussing research sponsored by the US DOT. Professor Jiang, take it away.
All right. Thank you, John, for the nice introduction. So I would also like to thank Professor Kang Osby for giving me this opportunity to speak through C2 Smart seminar series. So it's my pleasure to talk about the topic of learning-based control, which is very dear to my heart. So we've been working on learning-based control over the last 10 years. So the application to autonomous driving has started a few years back with Kang and my students. So today's talk will be decomposed in 2 parts: theory of learning-based control and application to autonomous driving. So let me show you a video first, and then I'm going to explain what is learning-based control. So you may have seen this video before, but I want to put a message. Mr. Sandman, bring me a dream. Making a student that I've ever seen. You'll have nobody to call my own. Please turn on your magic beam. Mr. Sandman, bring me a dream. Mr. Sandman, someone to hold. We'll be. All right. So from video, you see that the autonomous vehicle needs to make decisions to turn left, right, and to follow vehicles. So we are arguing that so the model-based control theory, what we learned from the traditional textbook, are not directly applicable to this scenario, because building mathematical models is time-consuming and costly, and does involve a lot of uncertainties. So for the real-time decision-making problem that I'm going to address for autonomous driving, so we need to figure out a different approach. So this approach we're going to call it learning-based control. So that means so autonomous vehicles or agents need to make fast decisions directly from input and output data. So mathematical model is only one way to to make decisions. That's the key to model-based control theory. But for some other applications, so whether or not we can learn adapt the optimal control law directly from input data is much more interesting. Of course, much harder. So we need to develop a theory that can put tools from different fields together. So we want this learning-based control law to address the fast response, stability, robustness, and safety with respect to other systems in the networks, and also to take care of robustness to to uncertainty or delays or loss of communications, for example. In the end, we want the controller to be near optimal. So in this talk, we are going to formulate this problem using the traditional optimal control problem formulation. So so the model, for example, the model of the physics systems is captured by these nonlinear differential equations according to Newton's law. So the model itself, is there, but we don't know the mathematical, expression of f. So we only have access to the data, input data like u, the control input, and the states like x. So we want to use data to learn a controller that eventually will optimize or minimize this integral, cost function called j. So when we look at the model-based control literature, this problem has been studied, but not fully. So if the model is linear, suppose that f is linear functions or linear systems, there are many published papers in literature by so many people. But when f is unknown and highly nonlinear, so we could not find any paper that provide a systematic solution to this problem. So to be safe, I say almost none. So objective of this talk is to show that by bringing the technique from dynamic systems, machine learning, and control theory, we should be able to develop a systematic solution to solve this optimal control problem and model uncertainty. So the traditional tool for this problem, is quite known, called Bellman's dynamic programming theory. But the Bellman's theory is powerful, but it has fundamental limitations. So people call them curse of dimensionality and curse of modeling. So which means computation time is exponentially growing as the state dimension grows. And also Bellman's dynamic programming theory assumes that the model is precisely known. So that's, of course, that's not the case in this talk. So we look at the past literature to see what has been done. So of course, so to address the curse of dimensionality and curse of modeling, then reinforcement learning is a model-free approach that has been used by by a lot of research to deal with the limitation of dynamic programming. So reinforcement learning is invented by Minsky in 1954. Biologic motivated by animal learning. So he observed that animals make decisions through agent and environment interactions, and try to improve actions by evaluating the reward, which is a feedback signal from the action. So you can continuously improve your action so that in the end the action you can find will be optimal, that will maximize cumulative reward. So that's the kind of problem. But this does not ask the agent to model the environment. So it's really a model-free approach. So of course the challenge is that how can you prove that the actions will converge to the optimal solution. So convergence is a big issue for reinforcement learning literature. So one of the big successes with reinforcement learning is the following. People know that in 2016, Google DeepMind team developed this reinforcement learning algorithm to beat the best Go player in the world, Seto Lee from South Korea. So BBC has the following headline: AI wins at Go, is the game over for humanity. So the application of driving this talk called autonomous driving is a much more complex challenge than static game, board game. Board game is of course complex, but if you put yourself in the context of autonomous driving, so the environment continues changing, dynamic changing, uncertain. So you don't know how many vehicles you are going to interact with. You don't know that the environment you are going to be. So this problem is much more challenging. So you have to develop a new theory. So learning-based theory is posed to address such challenges. So in the area of reinforcement learning approach to dynamic programming, there are a lot of papers, earlier days, written by computer science people and the operational research community. So for computer science people, they often assume that the state action spaces are finite. you have finite number of states, finite number of actions. So this is of course applicable to both games, and also you can use marketing processes to model so processes. So operation research community generalize them to infinite space, but assume that you live with a countable. So this is called countable infinite state action spaces. So for the application we are going to talk about today, so we live with continuous and infinite. So it's not countable state input spaces. So here's the brief history of dynamic programming, followed by reinforcement learning and approximate dynamic programming. This is not until 2010 that the field of control theory started to be merged with reinforcement learning to address the stability issue for continuous and dynamic systems. So this theory pioneered by several people. So Frank Lewis is one of them. He worked on this adaptive dynamic programming, assuming that the model is unknown, but structure, but it involves unknown parameters. So in 2012, my group at NYU, we generalized adaptive dynamic programming to robust adaptive dynamic programming to include not only parametric uncertainty in the dynamic processes, but also we talk about a mismatch between the model you use for learning and the real plant that you can control. So you have dynamic uncertainty. So then today I'm going to present our progress along this direction. All right, so I'm going to briefly mention the theory in the first part. What is the robust adaptive dynamic programming for continuous time linear systems, nonlinear systems, and eventually extend it to uncertain systems. Then in the second part of the talk, I'm going to talk about application to connected and autonomous vehicles. And finally, I'm going to conclude. So all the mathematical details and control designs can be found in our recent tutorial paper that was published last year with my two former PhD students. All right, so let's talk about the linear system first. So this problem is very classic, in control field, so-called linear time invariant systems. So assuming AB are constant but unknown matrices. So I heard about this data-driven control problem from a planning talk at 2009 Asian Control Conference. So the speaker, addresses problem. So try to say, using reinforcement learning technique to learn, gradually, optimal control law, taking this form, U equal to minus kx. That will eventually minimize, this linear quadratic cost. So originally this problem was posed by Kalman in 1960 when models is completely known, when AB matrices are known. So this theory is called the linear quadratic regulator control, LQR. So the optimal control exists under some standard system property, observability, controllability. So I'm not going to repeat them here. So the controller will take a following structure. So optimal controller K star will be solutions of the Ricardo equation, which is matrix equation. So if A, B are known, even though the optimal controller exists, but it cannot be implemented because implementation of the optimal controller depends on precise knowledge of A and B system matrices. So the question that how can you learn suboptimal controller? Just we want to come up with a good estimates of these system parameter or controller parameters from the data. So there are two methods that can be used. One is called policy iteration, another called value iteration. So these terminology are common in the literature of dynamic programming. They are recursive method that can be used to solve Bellman equations. So we are going to convert this method to the data-driven context when the system model is not known. So let's review the seminal work by Frank Lewis in 2009, where he presented his planning work about data-driven control. So his idea that you have to assume you have a knowledge, initial knowledge of a so-called stabilizing policy. Then you apply the policy, you can collect the data. You collect data, then you can evaluate this policy through something called a performance evaluation step. So you have to solve this equation called integral reinforcement learning equation from data. Does not depend on the knowledge of A and B. So how do you obtain these equations? So it's quite easy. So you just differentiate the left side quadratic function along the trajectory of the control systems over this time period from t to t plus delta t is the data collection period. Then you take integration both sides, you will obtain this integral reinforcement learning equations, okay, which is similar to the equation in the literature of reinforcement learning. Okay, so integral because you have to integrate along system trajectory. So then you have to update, you have to improve, okay, come up with improved policies through performance improvement step. So kj plus 1 will be, okay, now depending on the solution to the matrix equation pj. So under some mild conditions, Frank and the student can prove that, as a learning step j goes to infinity, pj will go to the optimal solution of the Cardi equation, kj will converge to the optimal solution that solve the linear quadratic regulator problem. Okay, so unfortunately, okay, now his solution depends on knowledge of B, because for the performance improvement step, the knowledge B is assumed, even though A is unknown. So nevertheless, this is a huge step, okay, now towards, okay, learning-based control. So you relax, okay, now the complete knowledge of the system models. All right, so I gave this problem to my student, first PhD student on, at the NYU Tandem, so Jiang, so to work on the extension towards a completely unknown kind of linear dynamic systems. So actually, it took us 1.5 years to solve this problem. So we published a paper in Automatica 2012 to say that, we needed to implement different kind of policies, either off policy or on policy, which requires the addition of exploration noise. Okay, so in front of this paper, it's just policy is equal to exactly a kind of on policy strategy. So that's the difference. So as a consequence of this difference, you can see we're going to obtain new integral reinforcement learning equations that combines both steps, performance improvement step, performance evaluation together into one equation. So now you see that AB knowledge is completely removed. So we can solve for unknown PJ and the KJ plus 1 directly from the linear equations. So now if we try to accumulate data over multiple time periods, we are going to get the many linear equations. So when we stop collecting data until you can find a unique solution to these linear equations. So that's something we learned from matrix theory, okay? So if we rely on those linear equations that we created over multiple data collection period, so we are going to write it into matrix-based form, linear equation form. So you can find, solutions to the unknown parameters based on data. So theta k is the data-based matrix. Cosine k is also data-based matrix. That depends only on the data, input data, and the state data. So you can find a unique solution when the data-based matrix theta k is full rank. Okay. So how do you guarantee this mathematical condition? Okay. So basically that's key. You have to add experimental noise carefully so that data-based matrix will be full rank. Okay. We have stated such condition on papers. And then we can prove mathematically, okay, now as learning step k equals infinity, pk will converge to the optimal solution of the Cardi equation, and kk will converge to optimal gain that solves the linear quadratic regulator problem. And if you turn off noise, you can calculate stability and subtotal optimality. So mathematics is very, very simple filter based on the linear algebra, okay? So the next problem we consider is that, if we don't know model, how can you assume you know an initial step-by policy? So this is okay now the restrictive assumption in the policy iteration step. So can we remove this one? The answer is yes, we can. Okay, so we can use the value iteration method to remove this hypothesis. So when we look at the literature, to our surprise, that there are much less work on value iteration for continuous dynamic systems. Why? Well, mathematically, the conversion proof is much harder, if not impossible, for continuous time decision making based on value iteration method. So that's where so problem is harder, and it remains to be open. So I gave this problem to my second PhD student, Tao Bian. So he solved this problem. So we published 2 record papers, one for linear model in 2016 and nonlinear model in 2021. So we use some advanced mathematical technique from stochastic systems and control. So one fundamental result is called stochastic approximation theorem. So in the interest of time, I'm going to skip the review of value iteration based algorithm. So, but I just mentioned that in my other collaboration with Professor Daniel Wolpert from Columbia, computational neuroscientist. So we discovered that value iteration mechanism is what the human brain uses for coordinating the body movement. So that's not the issue. So we're trying to validate this approach using experimental data. All right. So the natural question we ask ourselves is that, can you generalize this data-driven approach from linear to nonlinear? The answer is yes. So we did it in the past. And very interestingly, so we observed the fundamental difference between model-based control and learning-based control. So from a data science perspective, learning-based control method does not make a distinction between linear and nonlinear models. So same methodology can be generalized quite straightforwardly from linear to nonlinear. That's pretty intuitive because data is data. Doesn't matter data generated by linear model or nonlinear model is data. So how can we achieve this mathematically to make sure that the methodology remains the same? So of course, the proofs of stability, proof of convergence will be much harder, but that's a different issue. But the design, from design perspective, it follows the same line of reasoning. So I show you. So for nonlinear model, the optimal solution will come out of the partial differential equations known as Hamilton-Jacobi-Bellman equations, which is a PDE. So you can solve PDEs recursively using policy iteration method, model-based. But the problem that the gradient is not easy to compute, and the policy is highly nonlinear. Depends on the unknown dynamics, so it's not easy to find. So the trick that so you can approximate, nevertheless highly nonlinear. You can approximate these nonlinear functions using neural network approximations over some compact set, bounded and closed set. The set can be as large as possible. So as long as you take the many neural nets, so this is phi I, psi, theta I. So these are the known nonlinear functions. So you can reduce the the search for unknown function down to search for linearly appearing parameters. So this error term can be made as small as possible as long as you pick up a large n. So as long as the number of neurons is larger, then the error, approximation error, can be made as small as possible. So that's the key idea. So you see that the learning-based control now becomes the same. It's called linear-like problem. So even though the state variable, input variable appear nonlinear, but they are known data. So what is unknown is the set of unknown parameters, weighting coefficients. So we can apply same methodology we introduce for linear model towards estimation of these unknown parameters in the context of nonlinear control, nonlinear systems. So I'm going to skip the details. So basically, you can implement data-driven policy iteration method. You can also prove convergence. So parameter estimate can be evaluated using database matrices. So matrix must be invertible as long as we add suitable exponential noise into the learning process. So basically, you can convergence can be proved mathematically. So the difference that for nonlinear model we can prove only something called semi-global stabilization results. So the convergence and the stability hold only over a large domain of attraction, but this domain must be bounded. Can be large, but must be bounded. Okay, so that's the difference. Okay, with the linear case. So then you say, okay, so learning can be made nonlinear. How about robustness? Is learning robust to to model mismatch or to dynamic uncertainty? Okay, so here we spent a few years to work out the solutions. So what do we mean by model uncertainty mismatch between model and the prompt, or also called the dynamic uncertainty? So basically, you can decompose the real prompt into model. Okay, so I know the model. Okay, second order model, third order model, but the real prompt I don't know. So the mismatch are called dynamic uncertainty. So as a consequence, I don't know the dimension of Z. Okay, so you can choose a lower dimension model for learning, but you don't know mismatch. So I'm going to call Z dynamic uncertainty with unknown dimension, which may be huge. Okay, now. So then you eventually, the learning has two objectives. You want to achieve adaptivity and optimality with respect to ideal environment without dynamic uncertainty. Then you have to achieve robustness to dynamic uncertainty in a non-ideal case. So how to prove your learning is robust to dynamic uncertainty? So here there's a tool which you can use to prove robustness for interconnected systems. So basically, so there's an interconnection between dynamic uncertainty and the model. So this is the instability mechanism. So interaction is not good, even though both systems can be assumed stable. But when they start to talk together, you can generate unstable network. Okay, so this is an interesting phenomenon observed by a lot of people, in power systems, in industrial processes, in any network of robotic systems. So you need to introduce additional conditions to guarantee that interaction among system components will not destroy total network stability. So there are many conditions, to guarantee the total stability. So one condition that I developed with my course or my advisor in particular, during my PhD times, this so-called small gain theorem. So the composition of the gain, so each system has a gain, input output gain. So that represented the signal, incoming signal, outcome signal, how much outcome signal may be amplified or decreased from the incoming signal. So both signal gains, gamma 1, gamma 2, can be nonlinear, can be also linear. So for nonlinear gain context, so small gain condition states that the loop gain, if signal travels through the two interconnected systems one time, so-called loop gain, if composition gain is less than identity function, so basically the network will remain stable. So this is sufficient condition to guarantee the interconnected system will remain stable. Okay, so in the context of learning-based control, we have to train the data, train the model, train the controller, so that the gain gamma 2 can be made as small as possible. So this is a feedback-driven, data-driven idea. You want to use data to train controller so that the gain can be assigned to the bottom system. So the gain can be small. Eventually, you are not going to destroy the small gain condition. So if gamma 1 is fixed, but gamma 2 can be made small, and then the robustness will be guaranteed. So that's the idea. Okay, the idea is related to contraction mapping, which is fundamental tool in functional analysis. So we also apply this problem to connect the large scale power systems. So I'm going to skip applications, but let's mention that all the theoretic results and applications can be found in our 2017 book published by Wiley and IEEE Press. So, and also after publication of the book with my other students, we have generalized this robust adaptive dynamic programming towards other kind of classes of systems and other control problems. Basically, we can consider tracking, we can consider stochastic systems and periodic systems, and even multi-agent systems as well. So now it comes to the second part of this talk. So I want to show you how we can use learning-based control methodology to address challenging problems arising from connected and autonomous vehicles. Okay, so let me start with the first application scenario, so-called vision-based ladder control for mobile self-driving vehicles. So that's vehicle in our lab. So we have a camera installed, which is sensor, onboard sensor. So objective is that you want to use the measurement from the camera only to design control input for the vehicle. So here it's like linear velocity or angular velocity for the vehicle. Okay, so you control the steering angle, you control the speed. So the measurement we're taking from camera. So basically, camera we detect the edge of the road. So these are the yellow line. So the reference trajectory will be the green path. Okay, based on the camera measurement. So based on the current state and orientation angle of the vehicle, and the learning algorithm will be applied to figure out the turning angle for the vehicle. So the vehicle will be driven towards green path, okay? Turn left or right. So we're not going to do it manually, okay? With respect to the currently available controller based robotics literature in particular, people use a PID controller, but that's not the PID controller. But PID controller requires you to fine-tune manually the PID controller parameters. So here, all these parameters will be tuned online using data, okay? So that's the objective of learning-based control. So as the vehicle collect the data, it's going to tune the parameters. So you collect data so that the vehicle will be able to run optimally around the center of the lane. So that's the control objective. Okay. So let me show you the implementation of the controller, so lane keeping problem. So for the first iteration, we apply the value iteration approach, which may not be stable. So we do offline learning, but nevertheless, data can be used to update the control action. So after certain iterations, the vehicle can run around the center of the lane. And after 10 iterations, the behavior of the vehicle and the learning-based controller is almost optimal. Optimal in the sense that minimize the integral linear quadratic cost. So we can also do car following. So it involves more than one vehicles. So we want to the autonomous vehicle to follow a leader vehicle, which might be human driven, maybe it might be autonomous vehicle as well. So to make decision on that, data. So camera will measure the vehicle distance. So based on that, you have to adjust the control for the autonomous vehicles that you're not going to run past into the leading vehicle, and also at the same time you have to minimize the vehicle distance. So minimization of course, increase network throughput, and it's going to reduce the resistance for the following vehicles to the stable energy. So we use this linear quadratic gradient approach to design a data-driven controller. All right.
Hey, Professor Jiang, I just wanted to say, when that video was playing, it was tough to hear your words. So if you just want to repeat what you mentioned during the video, go ahead.
You cannot hear my voice? Okay.
Yeah, when the sound of the video, yeah.
Okay. So for this video, I just said that the data-driven design methodology can be generalized from one vehicle to a platoon of vehicles. So the objective of platoon vehicle is that you want to design autonomous controller so that the inter-vehicle distance will be minimized to increase the network throughput, to reduce our energy consumption, because the air resistance to the falling vehicle will be small, especially for trucks. So you can save energy, increase the network throughput. So everything must be done, from the data. Why? Because it's difficult to measure to mathematical models of the environment, neighboring vehicles. So everything done from data. So that's the advantage. So we also did implementation on the collision avoidance. So you put the collision on the way to vehicles. Vehicle will detect the object, and eventually have to redesign controller based on data alone. So let me show you a video. All right. So we also run the simulations with the Sumo for mixed traffic environment, which means autonomous vehicle will interact with a human-driven vehicle. So the blue vehicle are human operated, the red vehicle are autonomous vehicles. So you can design controller autonomous from data. So the objective is to keep, for example, the string vehicles optimal way to minimize inter-vehicle distance, and also to guarantee stability of network, which means there's no crash between them. So let me show the simulation. So of course, for this mixed traffic environment, we don't know the mathematical model for the human driver. We don't know the model for the vehicle. So we just use the inter-vehicle distance and the vehicle-to-vehicle communication to design the learning-based controller for autonomous vehicles. All right. So we also did the robustness analysis as well. So which means that when vehicle, the leading vehicle suddenly stops or accelerates, so can autonomous vehicle still accommodate to the behavior, can still maintain something called string stability. So we simulate the environment using sinusoidal disturbance signals. It turns out that the string of vehicles continue stable. Also consider merging of two platoons, splitting of two platoons into multiple sub-platoons. So these are implementation. I think my time is running out a little bit. So let me try to show you the data efficient part. Then I'm going to conclude. So one question that people keep asking at the conference is that is the learning algorithm data efficient? So can you do better job than traditional AI algorithm? For real-time decision-making problem, such as autonomous driving, so efficiency, data efficiency is the key. Stability is the key, data efficiency is key. So you want to make decision based on small sample data, not huge data, because we don't have such a luxury to collect data, because we have to make sure that during the data collection period, your controller will remain stable. So we show you the comparison. So I try to implement our learning-based algorithm on this classic or benchmark computer game called Flappy Birds. So this video I downloaded from internet, left side video. So that the flying bird how to fly across number of unknown obstacles through agent environment interaction. When the further touches obstacles, of course, one learning try which is failure. So you have to start over and learn again. Okay. So if you watch video for more than 2 hours, you're going to see that eventually both learn how to fly across the obstacle. But for our video, you're going to see that much fast. So you converge the steps in less than 10 minutes. So occasionally it's going to touch obstacles, so it's going to fail, but we can use the data, start over, update controller. So this is a difference. So it's not totally model free. So our learning-based controller uses techniques from system, dynamic system, and computer theory. So that's why it's much better performance and the traditional model free reinforcement learning approach. All right. So it's time to conclude my talk. So what is learning-based control? Now I can answer the question myself. So learning-based control tries to bring 3 topics together: dynamic systems theory, computer theory, and AI machine learning. So especially for the connection between AI and machine learning, in this talk we show you that using machine learning technique, especially reinforcement learning technique, we are able to design better data-driven controller that achieves adaptivity, optimality, and robustness. Okay, so vice versa, I have a new student working on the other direction. So control theory can be applied to improve AI algorithms. So you can treat AI algorithm also as, to some degree, as a dynamic processes, maybe discrete time systems. But the control theory provides a tool that can analyze, for example, robustness. So recently, one of my students worked on just published paper in a AI conference. So, and if we want, you can download paper from the website of the conference called Triple AI. So connected vehicles is only one of the many possible applications for this theory. So this theory should be applicable to network systems. So connected autonomous vehicles is one application. And you can find details from my, from our tutorial paper, that was published last year, in Foundations and Transit System Control. So I have to acknowledge support from NSF and C2 Smart, and also the collaboration with my colleagues, Frank Lewis, Cosby, and the students, and my students. They did a lot of work for this topic of learning-based control. Actually, I learned a lot from them. Okay. So having said that, let me stop here. So for any questions, you may send them to me by email. So I also try to respond questions by email. So thank you so much. Any questions?
Okay, thank you very much, Professor Jiang. Professor Jiang said we had some time for questions, so I'll encourage all participants to use the Q&A box at the bottom of the screen. I'll quickly take this opportunity to mention to our participants that if this research is exciting to you, the C2 Smart Center is always on the lookout for industry and agency partnership opportunities to maximize the impact and reach of our research. And if you're interested in getting in touch, you can reach out to c2smart@nyu.edu. So as I said, please type your questions into the box. And I guess what I said before will lead us into our first question, Professor Jiang. What comes next for this research, and what kinds of resources do you need to test this in the real world? I guess also what type of agencies or companies would you ideally partner with?
Good question. So right now, so we are trying to develop connections with the industry, especially Ford, for example, and some private company like Mitsubishi, and also some startup companies. So that's one collaboration. At the same time, we are trying to work with DOE labs. So Con is involved. So we try to secure some sustainable funds for research. So, and of course, NSF. So we work with different NSF programs. So especially civil engineering and electrical engineering programs. So I've been getting support from electric side. So I hope to to write proposals to civil engineering programs, so that we can bring in more students who work on this topic.
Okay, so we have a couple questions from the audience, which is awesome. Thank you very much for sending these in. So if I get this wrong, you can just feel free to retype the question, and I'll try to ask it again. First one is, so this is, I guess, from about 10 minutes ago. What would the objective of the leading vehicle look like in a platoon? Keeping it on track or following the center line? Did I articulate that right? Do you understand what I'm asking, Professor Zhang?
What would the objective leading vehicle look like? Okay, so here for one vehicle, we can use vision-based ladder control to control the motion. Okay, so to run at constant speed, for example, to stay in the center of the lane. So, but for the string of vehicles, so we assume that the motion of leading vehicles is known. So the following vehicle will have this objective to maintain the minimal inter-vehicle distance. Okay, so preceding vehicles, and also we want to guarantee that there's no instability phenomenon like a string instability, which means that the disturbance from the leading vehicles will be propagated through the string. So that phenomena should be avoided. So using autonomous vehicle, you should be able to dampen the propagation noise or disturbance from leading vehicles.
Okay, what about the scenario where the model dynamics is not accurate for learning-based control?
There are many scenarios. Okay, if you talk about the autonomous vehicle, I mentioned that you don't know the human driver behavior. For example, you don't model the environment. For example, you don't model the other vehicles, surrounding vehicles. You just collect data. Okay, so that's the model uncertainty. So if you go to the biology, life sciences area, like for example, computation neuroscience, that's the area. I have had publications from a learning-based control perspective. So we see that the human brain tend to do the same thing. So using learning-based approach. So when you grab, for example, object, when you try to reach object, when you try to finish a task, for example, so brain, that's an observation made by computational neuroscientist. Brain does not try to model the environment. For example, brain does not say, okay, how big is the object I'm going to grasp? What is the weight? So brain doesn't do that. Brain will say learning based. I give a try, then eventually I'm going to update the actions through reward function. So trying to minimize or some cost or optimize or maximize some reward. So that's type of learning based thinking is used in computation neuroscience. Okay, so so there are so many examples. For smart grid, same thing. Okay, smart grid, you don't know the mathematical model for distributed generators that your neighbors implement. You don't know when they're going to turn on and off the distributed generators. So what do? Well, I don't care. I just do learning-based control. So I mean, when the distributed generators are connected to the electrical networks, I can collect data. So there's so many examples. So I mean, you're talking about large scale systems, model reductions idea, internet congestion control. So the model is so complicated. Internet, network of computers, so large. So, but in the literature, people say maybe you can apply, model reduction idea to come up with simple model that can mimic the behavior of internet congestion control, for example. So then, from data-driven point of view, so the mismatch between the model used for prediction and the real model. So this one I'm going to call dynamic uncertainty. So eventually I can show you that this mismatched dimensionality cannot be neglected for kind of past guarantee. Okay, no. So the reason that so this should be taken into account. So learning-based control so has this objective to provide guaranteed robustness to mismatch, dynamic mismatch. Okay, so we can prove mathematically. So that's something computer science community now starting care about convergence proof, care about stability proof. So that means mainly they are talking about the Abelard function, same languages that the control people have been used for a long time. Okay. I hope my answer is good, even though it's long.
So we have another question. Can you talk a little bit more about applying RADP to potential network problems and give an example?
Okay, this problem I just answered already. So like a smart grid, for example. So in the talk I mentioned, interconnect the multi-machine. So it can be applied to smart grid as well. So transportation is one example because so anything that is composed of network systems can be applied. So we applied to distributed control also. So I mean in the book that I just cited, we mentioned learning-based decentralized control for a lot of engineering examples. So there's one question I should answer here. So what's the advantage of ADP over RL? So this is a good question as well. So as I said, so reinforcement learning and ADP, so even though they carry different names, because control system community are in favor of ADP, but the computer science people are in favor of reinforcement learning. But actually, they're trying to solve the same problem. Okay, they're trying to solve the same problem. So try to solve so-called decision-making problem. Try to optimize cost function. Through control update. So the difference is that by the adaptive dynamic programming, you really care about the convergence proof and the stability proof when you close the loop, when you try to close the learning algorithm with the physical layer systems. So for learning, so software layer, then physical layer. So, but then it's a control problem. Okay, so ADP must address this problem. Even though your learning algorithm converges, does not imply your closed loop system will be stable, because computer science people, in the past, they don't care about stability. So now for physical systems like autonomous vehicles, we do care about the stability and robustness. So that's the objective of control people. So control looks like simple, achieve three objectives: stability, performance, and robustness. But each of these subjects is very tough as a system grow complex. Okay, so that's the difference. So there's more to be done. So I never mentioned the deep learning. So we're working on that one too. So I think there are more open questions than the available answers. So autonomous driving is one great example. There are many other examples that for which we need to develop a new theory. So we have two additional questions.
Yeah, we have what's the maximum number of vehicles in a platoon that can run stably with the learning-based control approach?
Okay, again, that's a great question. Okay, so if you pay attention to the controller design, so how many number of vehicles? So as long as we assume that the vehicles can talk to each other within the platoon. Okay, of course, this assumption is very ideal because communication does have a range. Okay, so if we do allow for centralized communication, then centralized controls are applicable, then the number of vehicles can be large. But of course, nothing is perfect. You don't have a kind of communication protocol that can allow you to talk beyond communication range. So we have not specified the exact number of vehicles. But if you're talking about the vehicles running on highway, one-dimensional trajectory, then the range of communication is the number of vehicles you can tolerate. outside range of communication, you have to adapt our theory to a distributed learning control framework. So we are working on that one. So we don't have a lot of resource. Okay, now for then you are going to have global communications, then global control. So this is a very, very interesting topic.
All right, we have time for one last question. What are your suggestions for calibrating physical parameters like speed and steering range?
Suggestions, okay? So actually, for the leading vehicles, we just assume that they are known. So how to choose them, it really depends on applications. I need to work with transportation people. From a learning-based control perspective, the parameters are arbitrary.
Okay, some quick ending notes. Thanks everyone for staying to the whole time. If you enjoyed this webinar, definitely follow the C2 Smart Center on Twitter, join our LinkedIn group and our mailing list. Our next event is going to be a panel on the role of microtransit in the multimodal ecosystem and includes the VIA Rideshare Chief Data Scientist. Lastly, please feel free to reach out if there's a topic you'd like to see presented more of. A huge thank you to Professor Jiang and to the UGAS DOT for sponsoring this research, and to everyone else who joined us today.